Let's just quickly do a very brief bio of you and your background.
Oh, a bio of me. Well, I've been doing lots of research in the last 25 years on all sorts of topics. But for the last 12 years, I've been going 24/7 into astronomy research, and thanks to the fact that I can read in 5 languages, I've been able to read lots of material, lots of volumes of books of astronomy in original language, and that has helped me to get a nice overview of heliocentrism, actually, because heliocentrism only came about, in after Kepler, Galileo. Everyone before that thought that we lived in a geocentric system with the Earth in the middle, but as very few people know, for 1 century after Tycho Brahe's death. So Tycho Brahe is the man, the Danish astronomer whose model I've based the TYCHOS on. It's obviously, that's why it's called the TYCHOS. It's in honor of the great Tycho Brahe, we call him in Sweden. And he had an island which is now between Denmark and Sweden. He had an island for himself, the castle. He was his friend with the Danish king financed him generously to make an incredible. This castle was considered the NASA of the time. He had a huge budget, so he made fantastic instruments to watch the skies with. So I'm Swedish, like Tycho Brahe was Danish, because Denmark had conquered Sweden at the time, but then it went back to Sweden. So I kind of consider to have finished Tycho Brahe's work with this, because so I was saying that his model was considered, it was the ruling model for one century after his death. It was the one that even the church accepted, actually. And many people don't know that. It took a long time before the Copernican system model was accepted. Right?
But hang on, hold on, Simon. So you're saying that for about 400 years or so since Copernicus, astronomers have been getting it wrong.
Yeah, well, there's the underlying that's the underlying statement of the TYCHOS. But what I just said was that the Tychonic model, which we were going to look at soon. Let's first look at the one we all know. This is the Copernican or Keplerian heliocentric model.
And I just want to make sure that I follow. I'm going to keep interrupting from time to time if that's okay with you. But so just to make sure, we're talking about the model where everything orbits around the sun and the sun is the center of the galaxy.
That would be the heliocentric model, which we all learned at school, right?
Right, okay. And that's based on Copernicus?
Yeah, it was Copernicus who first came up with this idea, at least there was apparently some Greeks, many in the ancient times had also thought that the sun was in the middle, but it was a very novel thing to say that the sun was in the middle in the 15th century when Copernicus came up. So anyway, but he has been accepted now. We have the sun in the middle and beautiful elliptical orbits. You see here Mercury, then Venus, and then the Earth, right, in the third lane. The Earth has this moon around it. And it's pleasing to the eye. It's simple. It looks simple because we have, these concentric circles. And maybe that's why it's so much accepted. But it isn't that simple, and this, as I've shown in my book, because I have this book called the TYCHOS, our geoaxial binary system. Here, you can read it here. That's because the Earth is in the middle, but it's not stationary like Tycho Brahe had it. He stopped at the idea that the Earth didn't move at all, which is not very logical, because everything in the sky has an orbit. All stars have orbits of their own. All planets orbit. So why would Earth be the only stationary thing? So that's the first thing. But anyway, so this looks very complicated right here, but what we are looking at here is the result of the tracing function of the TYCHOS simulator, which we are going to look at later on, and which is a simulator which simulates the TYCHOS very well, perfectly. It is absolutely in accordance with every single observation made over the centuries. So let's go forward. This is to show that it shouldn't be so strange to see all this, trochoids, we can call them, these funny shapes, because this is what the stars look like today. This is from 2010. These are astronomers looking at stars hosting exoplanets, and they see these kind of shapes, just like we saw here. So there's nothing strange about this. This is what we know today, that these are the kind of motions we see up in the skies. Just to put this thing.
Okay, so Simon, so let me just make sure I'm following at this stage. The core issue, or one of the core issues, is that mainstream astronomy, or the current model, the current heliocentric model, is based on stars that are impossibly big.
Yeah.
And this is a problem that Tycho Brahe was trying to solve.
Yes, his main problem was with Copernicus was that the stars would have to be incredibly far away, absolutely unthinkably far away, if Copernicus' idea was right, and he didn't like that idea. He said, so we have our planets here: Venus, Mercury, Saturn, Jupiter, and then nothing before we meet the first star. For huge amounts of and incredible distances, and that didn't sound right to him. Right,
yeah, I mean, I mean, the first star or the closest star to us is what? Alpha Centauri.
Alpha Centauri, Proxima Centauri, which is also a binary system. We'll talk about binary systems soon. It's very recently they discovered that even Proxima has a companion. So all the stars have companions. Proxima is supposedly 4.2 light years away, and light years is incredibly.
It's stupidly far.
Yeah, even the closest star is stupidly far. But now, if I may, I'll start. Okay, let's start this. These are the identical models of Tycho Brahe and Patani-Samantha. Patani-Samantha is someone I only learned about when I went to India in 2016. And I went to an old astronomer who gave me a book with this model, and it is identical to Tycho Brahe's model. And I was stunned. I didn't know very few people. I mean, he's got statues in India. People know him in India, but not even that much in India. But he's completely unknown, Patani-Samantha. But he, nonetheless, came to the exact same conclusion as Tycho Brahe. And what is the main thing here, which I've highlighted in red and yellow? It is the fact that the Sun, the yellow one, and Mars have intersecting orbits. And all appears during Tycho Brahe's time, in the beginning when he came up with this model, they were laughing at him, saying, but then they must crash sooner or later. The Sun and Mars must crash. Well, no, because they have a 2-to-1 relationship. It's a 2-to-1 ratio, so they will never crash. It's a binary system. And exact same model Patani came up with, and he is considered a genius, one of the biggest ancient. I mean, he was actually he lived in the 18th century, but I don't think he copied Tycho Brahe's idea. He worked completely independently in the forest. He was detached from the Western world, but he came to the same conclusion, which is Mars and Sun intersecting. Their orbits are intersecting, and the rest of the planets go around.
But how's that possible that they intersect? Is it just the? I mean, if the sun, go on.
No, it's no intersection. It's just that they are overlaid. I mean, their paths seem to be intersecting if you trace them, but they will never touch here or here. They will never crash because it's a 2-to-1 relationship. When Mars needs 2 years to do one turn, and the Sun needs 1 year, so they will never touch. It's mathematical. So we now really need to get into the question of binary systems. Binary systems is something that people really don't know about, but it's amazing that people don't know about binary systems, because in the later 20 years, we keep discovering more and more and more. Today we know that at least 85%, actually it's more now, this is an old slide of mine, it's more than 90%, it's going to be maybe 100% of the stars in our sky are locked in double binary systems. So all the stars you see, folks, in the skies have a companion. I will say all. Okay, maybe I'm wrong, maybe it's 99.9, but let's say just all for the purpose of this course. So obviously then, statistically, the Sun can't be the only bachelor in the sky, right? He's got to have a companion, and the companion is Mars. And so this drawing here, I took it from an astronomy book, and I just put, well, what if this is Mars? This was at the beginning of my research. What if B here is Mars, and the center of Mars is Earth, and the Sun is here, A, B, okay? So that was my first postulation. So what I say here, what Tycho Brahe and Patani Samantha had unwittingly discovered was that we live in a Sun-Mars binary system. But they didn't know about the binary system. No one had seen any binary system. The first discovery of a double star was far later in 1650, or even later. 1650 was Riccioli. But anyway, long after Tycho Brahe's death, they discovered double stars. Okay, so here is William Herschel started looking at many double stars, and look at what he was. This is his first map. You can see how many red dots there. They're all double stars, and this is only in 1803. Already, this should have caused a revolution in astronomy. Oh my God! Almost all the stars are double, but somehow it has never been discussed, and most people don't even know that the stars all have a companion, which is amazing. So anyway, so here we are. This is my drawing of the TYCHOS model. We'll see how it works in the TYCHOSM simulator later on. But okay, so first thing I want to show you. Okay, we have the Sun and Mars intersecting. Okay, Sun here, Mars here. Mercury and Venus are the moons of the Sun, and I have proven this in so many ways in the book.
And Mercury and Venus are the moons of the Sun.
They should be called the moons of the Sun. I mean, they should be called because moons are very particular. Moons rotate extremely slowly around their axis, and so do Mercury and Venus. They rotate at walking pace. No other planet rotates at walking pace. like 2.7 for Venus and 5.4 for Mercury. Actually, one is the double of the other. And the moon, our moon, in 16 kilometers an hour, which is, it's like a 3, what is it now? 1:136 ratio. So the moons of our moon and Mercury and Venus, they all rotate very slowly. Now, another thing I want to quickly show here, you see Mars here. This doesn't mean that the Earth goes around Mars. This blue ring is my main contribution to Tycho Brahe's original model. I call it the PVP orbits because, and it lasts for 25,000 years, 25,344 to be exact. It takes 25,000 years for the Earth to move here. So this blue thing is kind of virtual. You just have to understand that we're not going around. It's Mars always passing here, and I'll show why later on. So the Earth, the PVP orbit is because, why is it called PVP? Because we are now under this polar star called Polaris, and in 12,000 years we'll be on the other side. Can you see my mouse? You see my mouse?
Mm-hmm.
Yeah. In about 12,000 years we'll be here, and we'll be under Vega, another big star in the sky, very famous star, Vega.
And then Polaris again.
And then back to Polaris. So it's PVP. That's my PVP orbit. And I mean, keep this in mind because this is what actually solves everything and resolves 41 questions of astronomy at the end of my book. It's all because the Earth-Moon system is moving around this PVP orbit very slowly at 1.6 kilometers an hour, which is 1 mile per hour. Okay? So here we see it from the side. Our system here, see? Here we are today, around the epoch 2000, with Polaris on top here. We have Polaris as a North Star. And we have Sigma Octantis as a South Pole star. In about 12,600 years, we'll be on the other side, and we'll have Vega as a pole star, and Columba. But this is not something that I've come up with. This is accepted by astronomy that we will have Vega in about 12,000 years. I've just made it, just made a system that shows it in a much more pleasant way, if you like, because this is just because we are inclined here. You see, this is Earth, inclined at about 23.4 degrees. We will kind of stay inclined more or less like that. Maybe we change 1 or 2 degrees over this ring. But anyway, it's 23.4 degrees. And we keep this tilt around this orbit. We slowly go around this orbit in 25,000 years. That is main point of the TYCHOS to understand.
That's very slow.
It's very slow. Yeah. But we have, very tranquil planets. We don't have incredible winds like on Mars, or we have a very tranquil planet. And so it shouldn't be surprising that we move slowly.
And there's no wobble.
This exactly. So how do heliocentrist astronomers explain this? This is the precession of the equinoxes, right? The fact that we change pole stars and we see all stars moving by 51 arc seconds every year. That's because we're moving simply around this. So here we go. This is what we have called for ages. We have called it the precession of the equinoxes. Well, it is the motion of the Earth, simply. So here we are today, on June 21, okay? We will have the sun here, but 2,112 years ago, we were here, and the sun was in Cancer. Now, in June, it's in Gemini, and in 2,112 years from now, we'll be in Taurus, because we have moved this much. All right? So you see this cake I've divided in 12 pieces. It's 2112 years. And by 12, it's 25,344. Meanwhile, Mars will always pass in the middle of the PVP orbit. And that's the most astonishing thing I only discovered after we made with my Swedish colleague. He's Patrick Holmqvist. He's a computer programmer, and he was able to do the simulator we're going to look at. And when the simulator started working, I finally understood why Mars was passing. When it passes closest to Earth, it is exactly in the middle of this orbit. So now a little philosophical interlude, because it goes to answer your question before. You said, we're moving very slowly. Yes. So, could Earth's snail-paced motion be a key prerequisite? How do you pronounce that in English?
Yes, that's correct. Prerequisite
for biological life and for any given planet's habitability. I mean, just think about it philosophically. Doesn't it make sense that we are moving slowly? That we're not going around at 90 times the speed of sound around the sun? Because that's what they are saying. We should be going right now. You're sitting on your chair there very comfortably, but you're moving at 90 times the speed of sound, Jerm. Do you feel it?
It's the numbers that they use are just absurdly big.
Yes. So anyway, let's get on. Now, the question is, do we have any similar system up there that looks like the TYCHOS? Oh, yes. We have this largest star in our skies. I mean, the largest, it's twice the size of the second largest star optically. It's not the largest star, apparently many are larger, but Sirius is the number one biggest star we have, right? When we look out in the sky. Okay, so when in the 18th century, around there, they discovered that Sirius had a companion, and they called it Sirius B, right? And Sirius A goes around here. See, it goes around clockwise. Sirius. This is the main star of the Sirius system, Sirius A. But then they discovered Sirius B, which goes like this, around a much larger orbit. Well, look at this, how this compares to our system in the TYCHOS. We have Mars, which is comparable to Sirius B. We have the Earth, comparable to Sirius C, which we will see later about, and the Sun here. And even the proportions between the nearmost passage of Sirius B and the nearmost passage of Mars and the farthest passage of Mars is 1:7. So it's a very, very similar system to ours. But what I really, I fell off my chair when I discovered that, they have been able to measure the proportion between the big one and the small one. Well, it's 205:1. That happens to be the same proportion as Sun and Mars. So this is why I can write, is the Sirius binary system the twin sister of the Sun-Mars binary system? It's not such a crazy question, because they are incredibly similar, right? Do you agree, Jerm, so far?
Yeah.
Right. Okay. So we don't have any system we have ever seen that's like the first slide I showed, with the Copernicus system. We have never seen a star with lots of planets going around in circles, in ellipses, perfect ellipses. We don't have a similar system in our skies. I tell you, we don't. And lately in astronomy journals, they're starting to talk about it. Is our solar system an outlier in the universe? Are we the only ones with that shape? No. We are like all the others. All the binary systems are like this. So, I mean, the logic of the TYCHOS is absolutely clear. So here is a little thing I put together. This blue image. You can find it on Wikipedia. It shows Sirius A and Sirius B, right? The tiny Sirius B and the big Sirius A. Okay, so what is Sirius C? It is something that they have not found in the telescope yet. They can't see it in telescopically. With telescopes, they can, though. There has been a large French study with the spectrometry that they have determined that yes, there should be a Sirius C, right? But it's so close to the big stars that we can't see it in any telescope because it's in the glare of the big star. Well, what if that's exactly the same case for, if you would be on Sirius, you would look down on our system, maybe you would see Mars, but you wouldn't see Earth because it's blinded in the glare of our sun, right? And as we saw, they are very similar, those two systems. So this might be what reality. I mean, if you take a spaceship to Sirius, you might see the same thing as we see Sirius, how we see Sirius. So here we come to the question of the suns, the moons of the Sun and Mars. I told you before, right, that Venus and Mercury are the moons of the Sun. They are the moons of the Sun. Yeah. And you know what? Mars also has two moons. Not many people know that. They're called Phobos and Deimos. So you see, we have husband and wife with two kids, whatever you want to compare it to. Very kind of balanced, couple. Both have two moons, and we have one moon. And we have a very large moon. The Earth has the biggest moon we know of, proportionately to its host planets. We have a huge moon. It's almost a third. It's 3.6 times smaller than Earth only. So we have a huge moon, and we'll look at the moon soon as we go ahead. So why can I say firmly that Mercury and Venus are the moons of the Sun? Well, oops, I don't have it here. I don't have this slide. But I tell you just here, because in the TYCHOS simulator, the way it works now, you can see their orbits. If you see it from the side, they are inclined, both orbits of Mercury and Venus, at 7 degrees. And do you know what? A mystery in astronomy is why is the sun's axis inclined by 7 degrees? Because it is. Well, the sun is inclined at 7 degrees and its moons have 7 degrees inclined orbits. So the Venus and Mercury are going around the sun's equator. Because it's a big unresolved question why the sun is tilted. It's supposed to be the central thing. Why are we all going around this equator? No. Only Venus and Mercury go around in the same plane as the sun's equator. And that came out only in the TYCHOS simulator. You can't see that in a heliocentric simulator. So now we get to the moon, which is absolutely fantastic. I mean, this is maybe also one of the most astonishing things of the TYCHOS. I found out that the Maya people, they knew that the actual average synodic period of the moon is 29.22 days. It's too long to explain now, but just accept this. 29.22 days is 1 here, okay? So that's the moon. If you multiply this by 4, you get Mercury's exact synodic period. Synodic periods means the time a body employs to get back to the sun, in front of the sun. Return in front of the sun, on the same line as the sun. Then you multiply this by 20, you get Venus's period. By 25 you get Mars, by 150 Jupiter, by 375 you get Saturn, and then all the way up to Pluto. They are multiples of our moons. Period, synodic period. So it's like a clockwork. It's a perfect clockwork. So I call the moon the central drive shaft of the clockwork, jokingly, but it's not a crazy way to define it, because it is here in the center. I mean, if the moon was just one appendage that's in the third lane went around the sun, why would it have these resonances with everyone, with all our planets? Okay? Just ask yourself this question. Here is another point. Well, I tried to take the slides that had maybe just an overview of the TYCHOS, because I can't really in 1 hour talk about 300 pages in my book. But this is another strong point. It's about Mars, because Mars was Tycho Brahe's problem. That's why he asked Kepler. Kepler was a young 26-year-old good mathematician, but he asked Kepler, help me with Mars, because I don't understand it. And it was the number one problem, Mars. Well, you can imagine why now, because it's the companion of the sun, so it's very special. So I boldly say here, the heliocentric model is geometrically impossible. Oh, how dare you, Simon? Well, here's one thing. The Maya people, as I mentioned briefly before, the Maya people were experts in Mars's cycles. And they found that Mars has this very strange cycle. If you look at Mars and you align it with a star, right? Jerm, you follow me?
Yes.
You're in your garden, you look at Mars, and you choose a star, and you say, let's see how long it takes before Mars comes back to that star. Well, it will be 7 days. And then again 707. And for 7 times 707 days, Mars will return in front of the star. But the 8th time, it will only take 546 days. Now go and explain that in the heliocentric model. Well, this is a heliocentric comparison from a heliocentric simulator we're looking at. So if it would be like that, we'd have Earth here, with Mars in front of a given star. I chose this control star called the Nebel Jetty. And 546 days is 1 year and a half, right? So 1 and a half, and we will be here, 300 million kilometers apart from the first observation. Yet, in reality, Mars will return in front of that same star. As if 300 million kilometers didn't do nothing. And how do mainstream astronomers explain this? Oh, they say because the stars are so far away that not even 300 million kilometers will make a difference. Maybe they're slightly, converging here. No, they are exactly parallel when you look at them. Actually, I've been testing various heliocentric simulators, the most famous simulators, which are this configuration. They actually diverge, so they can't say that. They diverge slightly. So anyway, so how does TYCHOS explain this? You must be wondering.
Well, before you go any further, so what you're saying is that the heliocentric model and the flat Earth model are wrong.
Oh, let's not talk about the flat Earth model, please. Please. No. Please. Spare me that. Okay. No, let me just continue here with Mars, because it's an important fact, an important thing. So here's how a heliocentric simulator depicts 8 successive conjunctions of Mars with a given star. I'm still using the Nebel Jetty as a control star, right? So this is what would happen according to the heliocentric model. So, 0, 1, 2, 3, 4, 5, 6, 7. 7 conjunctions with the same star, which is what actually happens. But all these lines are in different places. And they are all parallel. Well, they're supposed to reach the same star. Although Mars is much closer to the star. I mean, you know that there should be some parallax. If you put your finger close to your nose You only move your head a very little bit, and think of your finger as Mars. You move your head a little bit, and you'll see everything moving behind it. Well, Mars is very close, so this can't happen. And this, between 7 and 8, it's a famous 546 days. That's the shortest period Mars has, but it shows the Earth being the farthest away from one point to the other. Well, here is how the TYCHOS explains it, shows it. This is how the TYCHOS simulator shows it. Every single 8 of these 8 conjunctions are on the same line towards the star. All in the same line of sight. Why? Because the 8th time, you see this, see how Mars does, and it kind of does a spirograph. When the spirograph closes every 8th rings it does, it crosses this line. It's hard to explain it. You have to see it, and you can check it out on the TYCHOS simulator, which we hopefully will have time to look at. But anyway, don't you think this looks a bit more credible, Jerm?
Yes, and what happens here is that it makes a lot of mental gymnastics no longer necessary. No, but mostly you would have to say, if you would have to criticize. Someone pays you to go and falsify the TYCHOS. You would have this really tough task, Jerm. You would have to say that what we see here is just the result of coincidence. That all 8 dates line up on the same line of sight to the star. But in the TYCHOS, Mars goes at constant speed, and in circles, all the trochoidal circles. We'll look at trochoids later. So there is no, Kepler had to come up with variable speeds. All planets are supposed to speed up and slow down all the time. He had to come with these fudge factors to make it work. But no need for that in the TYCHOS. That's why the TYCHOS simplifies things. People think at first, it's complicated. No, it simplifies many things and does away with so many arbitrary things they had to add one up top of the other to make the geometry work in the heliocentric model. Okay? Now look here. What did I find in Kepler's big, famous, super famous book, Astronomy Nova? In the beginning of the book, he was playing around with this idea. He was playing around, but he threw it away. He threw it in the dustbin. But look, his work was to try to explain Mars, what Mars did in the sky, how it moved. Well, this was one of his first proposals, but he ditched it. But what do I see when the TYCHOS simulator starts working? It drew exactly this, what Kepler had calculated. He was a good mathematician, but he couldn't understand why those loops will happen, why it would move, why everything would move like this, because he didn't have computers at the time, so to see how they would evolve like this. You see, here he has Mars in 1580 and Mars in 1596. It's a 16-year cycle of Mars, which the TYCHOS perfectly. You can put this on top of that. It's practically the same. You see, and also note that he even managed to Kepler. He drew, this is thinner and these are larger. This is thinner and this is larger. Well, it's very, very good. And this is another question that I cover in my book, but why would it be different? But this is the geometry of the system. So here's what a trochoid means, just so people understand. It's nothing magical. It's just
a thing rotating around another wheel, a wheel carrying a thing and rotating around it. That makes it trochoid, and that's why we see Mars doing these things, and not only Mars, all the other planets do this, because they are all rotating around the sun, somehow magnetically attached, I suppose. We don't know. Is it Newtonian gravity? Is it electric universe? Is it maybe it's ether vortex that makes everything go around the sun? We don't know, and I don't pretend to explain this in detail, because this is not the scope of the book. The scope of the book is to make geometry match with observations, and those are hard and solid. We can touch them. I mean, they are in tables. Everything matches with the observations in the TYCHOS. So what I'm showing you here, I call it the man's yearly path, and this is also crucial to understand. So, what is this funny trochoid here? This trochoid, you have to imagine a man in London here. You see, this is England, this is London. I just imagine a man in London, an astronomer, at midnight. He takes a picture of a star here in March. Then, a month later, he takes another picture of the same star here in April. Always the same, 21st of March, 21st of April, 21st of May. And so you can imagine the time lapse. If you were hovering with a spacecraft above this guy, you would see him doing this, because the Earth slowly it rotates every day once, and it moves slowly from left to right here on the screen. So that makes a trochoid. So no astronomer has ever known this, so they don't know why they see stars doing, because this is what they see stars doing, as we shall see. So this funny shape is the reason why, first of all, why James Bradley. Have you heard of James Bradley?
No.
All right. James Bradley was, he became the royal astronomer. Well, he spent years looking at the stars. He had a big telescope in his chimney, and he looked at a kind of a polar star. And he was absolutely flabbergasted, because the star was moving in a way, completely unexpected way. It was moving like this, what we see here. Today, this is a modern depiction of what Vega does in 3 years. 1, 2, 3 loops in 3 years. Well, easy. This is 1 year. So you do 1, 2, 3. This is simply why Bradley saw this. But he had to come up with a very, very convoluted explanation. He called it the stellar aberration. You can read about it. It's absolutely incomprehensible. I still don't get it myself. But he tried to find an explanation, and when he found this explanation, it was hailed as a triumph of the heliocentric system. Nobody protested. Nobody understood it really, but they said, "Oh yeah, no, that actually proves that we are going around the sun." Yeah, right. But this is very funny. This is interesting. Do you know, Jerm? Do you know that our clocks only strike noon correctly 4 times a year?
I did hear that. Yeah, I did hear that. I don't know why though.
Okay, here you have the explanation. You've never seen it before, but here it is. So, this is the fact. I mean, this is the fact that the sun is aligned with us in these 4 dates: December 24, April 15, June 16, August 29. And another fact is that we can photograph the sun during a full year, and the sun will do this analemma, an H-shaped thing. And no one has really explained why it does this funny and asymmetric age because it's smaller up here and larger down here, right? It's a 3-to-1 ratio. Here is the explanation. We move it, by a factor of 3 here, and then we move backwards by a factor of 1, kind of backwards, right? So this makes, if you look at the sun on the side here, it will make this 8. Well, the 8 is, the height of the 8 is because in June, this is because of the tilt of the Earth, right? But why does the sun drift sideways? No one has explained that convincingly. They say it's because of the elliptical shape of the Earth's orbit. But no, it hasn't got this enormous elliptical shape. This is why. And look, see here, the 4 dates where the clock strikes noon correctly are December 24, April 29, April 15. They are on a line here. Here, you see, geometrically, it is a perfect match. And then June 16 up here. These are the 4 times where we are on this line. That means we are exactly aligned. Our clocks are aligned with this. But why are our clocks aligned only 4 times? Because our clocks go around in circles. I mean, constant speeds. We don't have clocks that can slow down or speed up. So we have just adjusted. We have invented the equation of time to make it work good enough for our daily purposes. So the clocks are okay, but they are only right 4 times a year. Just because we are moving around like this. This is the reason why. Because we move in a trochoid every year. You understand? This is 1 year, right? And here we go again, Vega. So here, now, the distances to the stars, which you asked about before. Still there, Jerm?
Yeah.
Yeah. The distances to the stars was Tycho Brahe's biggest problem. He didn't like the idea that the stars would be so far away. It didn't make sense to him. So how are star distances currently measured? Well, this is what they do. So they look at the star in June, right? This star here. They want to measure how far this star is, the nearby star. Nearby means, a star which is reasonably close, that we are interested to measure. And then we have very, very, very distant fixed stars. So they use this background and they look at the star and take a picture here, and then they wait 6 months. Okay, 6 months, you go around here. And then in December, they take another picture. And then they do the trigonometric calculation and say, oh my goodness, so it's very far away. But they are basing their idea that we move by almost 300 million kilometers sideways, right? 299.2. This is 2 AU, 2 astronomical units. This is a huge distance. Well, what does the Earth do in the TYCHOS? Only 14,036 kilometers a year, therefore 7,018 every 6 months. 718 kilometers is 42,633 times less. This is why in my book I dare say that the stars are probably like 40,000 times closer than currently believed. And
but if they
also
are
demonstrate.
But when you say the stars are closer, there would still be stars further than that.
Oh yeah, I mean, there are stars all the way. I mean, at every distance, of course. But let's just, if you look at our closest 20 stars, the most important ones. First of all, you'll notice that they are double. All our closest stars are double stars. Very, very few that still are thought to be single. Very, very few. This is an important point because I'm saying, how can the sun be a single star when everyone else is double? So, in the Copernican model, now we're going to talk about stellar parallax. Stellar parallax is what we saw here, right? They use this parallax angle to calculate the distance, right? So, But the problem is that in the Copernican model, where we supposedly go around the sun, so I've done a car here, jokingly, I've done as if you were in a car going around the sun, you would see the stars only out from your right-hand window all the
Hang
time.
on, Simon. Actually, the car can work because, as you well know, Elon Musk apparently sent a car into space.
Yes. A sports car. Yeah. Yeah, that's funny. People believe in that. It's amazing. But anyway, so this is a problem with the heliocentric model. Why? Because I'll tell you why now, shortly. In the TYCHOS model, though, we would expect both positive and negative parallax. What does it mean, positive and negative parallax? Well, it means that if you're in this system, you will always see the stars when you pass it going from your left to the right, From your left, in your window, left to right, not from right to left, because that means you would go backwards, which no one says we are going ever backwards. But in the TYCHOS model, since we're going slowly at 1 mile per hour around our PVP orbit, you remember my PVP orbit? We're moving very slowly. We've done a very small piece of this orbit in 1,000 years. So we're kind of moving in a straight line, and almost. And so we can see both types of parallax, a positive and negative. So that's expected in the TYCHOS. Here, it is illustrated even in more detail with the Mans-Yearly path. Remember my Mans-Yearly path? Well, see, if you decide to measure this yellow star here, between March and September, you will conclude that it has a positive parallax, because you have moved from, let's see now, as we look at the screen, you will have moved from left to right this much, okay? But if you decide instead of looking at this other star, which is close to this other, almost the same star, between September and March, simply reversing the 6 months, the choice of your periods, you will see that star having negative parallax, because you have gone backwards for a little piece here. That will be negative, and this will be positive. All right? And sure enough, in the European Space Agency's tables, they have. I'll show you now how they are distributed. I'll show you here. This is this. Let's first look at this. As of the official star parallax catalogs, 25% of the stars exhibit positive parallax, 25% exhibit negative, and the rest, 50%, exhibit zero parallax. They can't find any parallax. As if those 50% of stars won't be moving at all. But that's impossible. If we're going around the sun, they should move a little bit. But anyway, this is absolutely absurd in the heliocentric paradigm. What I wish to show you here, that this speculation here, people make, this is speculation. How can you prove it? Well, it was proven by Bessel himself. You see, the first time Bessel is famous for having found the first parallax of a given star, because for many, many years they couldn't find any parallax, and that was a big problem for heliocentrics. And Tycho Brahe was saying, see, you can't find any parallax, so we are immobile, we don't move at all. That was Tycho Brahe's point. But then Bessel came later on. Brahe was dead by then. But you know what I found in a book, hard to find, astronomy book, that Bessel, the first time he looked at this Cygni, which is famous for astronomers, Cygni was the first star with a detected parallax. Well, wait, the first observations he made of Cygni was between August and March, and he he saw a negative parallax. And that's stated in the book. Bessel was disappointed again. His results were negative. It must have been an error of the instrument. You know, they always explain away, oh, it was an error of the instrument. But he did see first Cygni having a negative parallax, a small one. But then he looked from between March and July, and I found these dates. I found it, and see, he got a positive one. So this Bessel, the guy famous for having discovered the first stellar parallax, proves my point. All right? Proves this negative, positive parallax point.
Yeah, that's a smoking gun, isn't it?
I would say so, modestly and humbly. I mean, what can I say? I mean, is this also a coincidence that I found this? And no one has explained why he first saw negative parallaxes. And then no one has explained why many other astronomers of the time kept seeing negative parallaxes. And they couldn't explain why. They couldn't understand it. And they can't understand it today because still in the modern tables. So here, let's read this. In the TYCHOS model, any given star can exhibit either positive or negative parallax depending on the time window chosen for any given parallax measurement. We saw that. This is due to a mass yearly path, our trochrate, remember? That's why. That's why it's complicated. But in the official modern tables, this is the distribution that we can find. If we are patient enough, as one Italian astronomer, he went through all the huge 1 million star catalog and he came up to this subdivision. Well, this is exactly what we would be expecting in TYCHOS. Here I explain why 50% of the stars will have no parallax at all. Because, see, Jerm, I mean, this is you, okay? This is not Joe, this is Jerm, right? Going this way. You're moving along our orbit very slowly, going away from the star. Well, if you go away from a tree, straight away from it, you won't see it moving against the trees behind it, right? It will stay aligned. And the same will happen. So if Joe takes a picture of this star in March and waits 6 months and takes another picture, he will see no parallax because he's gone away from the star. He hasn't moved sideways, you see? Quickly to show you how it's worked. If he takes a picture of star in March here, he wants to see a star here in March, then he does a little curve, but in September he will be on the same line to that star. So he will see no parallax, you see? Same in the opposite direction. If he wants to measure a parallax of a star here, between March and September, he will see no parallax at all, right? So that's why 50% of the stars are unmeasurable. They don't have any parallax. So we're reaching the end of my short, compact presentation here.
Yeah, I understand that what you're talking about is very difficult to compress into a space of about an hour, but I'm enjoying it.
Yes. Thank you. I did my best. I mean, it's really hard to condense such. So there are so many other things in the book that's I really hope people will read it. It's even available for free now in several languages on my website. So, but you can buy the hardcover book as well. It's very nice, and and you should read. At the end of the book comes I think that's the clincher of the whole model, because this is really something you can't explain away. You can't say that my Heliocentric chapter is a result of immense amount of coincidences. But shortly, so this is the green orbit you see here is Halley's orbit, the famous Halley's comet.
Which I've seen. I think I've seen
You've
twice.
Seen?
I think.
Oh no, you're not that old.
Oh no, wait, once.
Yeah, because it takes 76 years
to
come back. 75.7 exactly, as you will see in the book. And so the Halley's also, like all the other planets, even the comets go around in these trochoidal, orbits. This, mind you, we're seeing it sideways. It is not elliptical. It is, if you see it from above, it's exactly circular. This screen, everything is circular. There is no elliptical orbits in the TYCHOS. No need for elliptical orbits, which are absurd in my mind. So Halley's returns every 76 years. But do you know what they say officially? That sometimes it returns in 73 years, and other times in 79 years. Whoa, why would that be? 6 years of difference? Yeah. That's because of perturbations. When it comes close to Jupiter, it kind of slows down for 6 years. What is he doing? A kind of a sightseeing tour around Jupiter for 6 years? But that's what they tell you officially. That Halley's is chaotic. That doesn't have a regular period. Why do they think that? This is why. Now we're looking at the screenshot from the TYCHOS simulator, where Halley passes in a time span of 4 years. So when Halley's comes close to Earth, it can be seen here, 1, it can be seen here, 2, or 3, or 4. Halley's comet can be seen from the Earth for 3 or even up to 4 consecutive years. And that's why sometimes in the history, a guy saw it when he was here, sometimes another guy saw it was here. So they see these differences and they couldn't make sense of it. And so it's chaotic. But it's not chaotic at all. It's just the fact that they don't understand what it's doing, you know. It was seen 3 times in 1908, 1909, and 1910. Halley's was seen, but only one they identified it. They said, "Oh, that's Halley's," was this one, which came pretty close. The other ones, they gave other names to them. They baptized them with different names, and that has occurred for every single passage in known history. They have given other names to comets they couldn't understand. They were going in the wrong direction, compared to what they were expecting Halley's. So that can't be Halley's. We have to give it another name. And my book is full of. I have found up to 70 occasions where they have called a comet another name, but it was always Halley's. 70. You have to understand them by reading the book, because it's what I'm saying is that these 70 are, of course, we are going back. I mean, even back to 1,000, some date to 1,100 before Christ. There is an old tablet that talks about the comets, and that corresponds in the TYCHOS simulator to Halley's. So 70 examples of misnamed comets are in my research, and if you want to call that 70 coincidences, well, I think you're insane. Simply, right? I mean, there is a limit of believing coincidence. And okay, I had these extra slides, which I thought maybe I'll put these slides in. People will say, "Oh, but isn't Mars supposed to be a planet?" All right, but Mars is kind of reddish, right? So this is from a scientific paper. Can a star turn into planets? Yes, a star can turn into a planet, but this transformation only happens for a very particular type of star known as a brown dwarf. So I'm not saying that necessarily Mars is a brown dwarf, but it is. Brown dwarfs don't shine with their own light. No brown dwarf is visible in the sky. They're all undetectable with the naked eye. Despite its name, a brown dwarf that is still glowing does not appear brown. Rather, it appears magenta or reddish orange. Okay, sounds a bit like Mars. Despite beginning life as a star, a brown dwarf quickly uses up its heavy hydrogen, goes dark, cools, and spends the rest of its life as a planet. Sounds a bit like Mars could be one of them, but not necessarily. Just for food for thought. But we don't even know exactly what Sirius B is. Sirius B is 205 times smaller than Sirius A, and Mars is 205 times smaller than the Sun. These are things that awaken my interest. I don't know, I'm not so interested in qualifying what exactly Mars is supposed to be. Is it a red dwarf? Is it a planet? It's not important to me. And here is what I talked about before. This was absolutely amazing when I realized this. That when Mars comes as close as 56.6, this is the closest it can get. Every time, because it does it regularly, it is exactly in the middle of my PVP orbit, which I calculated independently long before this happened in the simulator. So that was a really nice, like a present that the simulator gave me. How wonderful. Mars is therefore, you could, here, it's like the pivot. What are we looking at here? I've just superimposed 4 screenshots separated by 6,336 years. That's 1/4 of the famous 25,344, right? So 1, 2, 3, 4. And Mars keeps passing in the middle of our PVP orbit. So here we have a start of trying to comprehend what is this? Is Newton's gravity still valid? Do we have to find some other? Yeah, I don't pretend. I don't have, I have no pretension to replace Newton's gravity laws. It may even work, but just in a different way. So, because that's the biggest objection. People say, you're going to throw away Newton's gravity. Oh, no, my goodness, no. You're crazy. But see, isn't this beautiful, first of all? What our system does in 25,000 years. And this is what the Sun does in 25,344 years. So here is our orbit. We are going this way. We are going clockwise. And the Sun is going counterclockwise. Okay? And the distances will never change. You will have to understand this. The Sun will never be this close, okay? Because when the Sun is here, we are here. So the distances remain exactly the same, the relative distances, okay? But so let me just, like a last philosophical thought. You will ask yourself maybe, so why are we going around in a clockwise direction? And the Sun and everybody else goes around counterclockwise. Well, you could imagine, a good comparison would be with cyclones. You know that cyclones and hurricanes on Earth, in the northern hemisphere, all cyclones rotate counterclockwise. It's called a cyclone. In the eye of the storm, everything is very, very, very calm. And actually, anticyclonic winds go clockwise in the northern hemisphere. Now, I've been checking, and it's not like the eye of the storm. They say the eye of the storm is very, very calm, and we have never seen exactly which way it goes. But we know that anticyclonic, very slow winds rotate clockwise, whereas cyclones, hurricanes, fast winds rotate counterclockwise. So it's like an analogy we could imagine, just to understand. Maybe we live in an ether vortex. The whole system around us is the ether rotating like a wind, and we are stuck in the eye of this storm. Just a philosophical thought.
Sure.
Oh, this is my last extra slide. I didn't think we could reach all this way, but I just put it in there because it makes me mad. I mean, this is what they are saying, that comets do cigar-shaped orbits, very, very thin, elongated, whereas asteroids, which are about the same size, I mean, Eros is just about the same size as comet Halley, about 15 kilometers of diameter. It also comes very close to Earth, like 0.1 AU. They come as close to Earth, both of them, but the one has this kind of orbit, and Eros has a practically circular one. What kind of universal law of gravitation would make two such similar objects have such different orbital shapes? Really, can anyone explain? Is there an astrophysicist here on board to explain this? Really, it is something that astronomers will have to address. And I'm saying that comets don't do this. They are doing round, even ovotrochoidal orbits, and that's what Eros does too in the TYCHOS. So maybe now I can show you quickly a little piece of the TYCHOS, which I've opened here. And so we shall put up, we shall look at the TYCHOS moving TYCHOS, and put on the trace, maybe, which put on the tracer on Mars. Maybe we'll go a bit faster. There we go, a bit faster. This is Mars leaving, the trace that it's doing. I mean, this is the trajectory that it does in reality. And so we will make these retrograde loops from time to time. We could go even a bit faster. Let's do it 3 months. All right.
So the sun orbits Earth.
Yes, the sun orbits Earth. It's still a very important object because it's the one that everyone rotates around, but the Earth, because we are in the very center. Yeah.
I can see the shape that it's creating.
Right. We can put Venus. Venus is traced now as well. Let's see. We can start again with both Venus and Mars, right? And
I can hear your computer fan working overtime there.
Yeah, of course. It's a lot of computer power needed here. And we can stop it here, and we can look at, we can change the time at will. It's a wonderful simulator. It really is the best.
Okay, you're back.
Right, Jerm? I dropped out.
Yeah, your computer was working overtime there.
Oh, yeah.
Okay, we are out of time, Simon.
Yeah. Yes.
So
can edit stuff.
If you don't mind, please give me a very quick summary of this conversation for those who might have struggled to follow. All right.
Well, yes, it is. It is for everyone to think about the very idea that we are just one of many planets going at hypersonic speeds around the sun. Is, to me, it's unbelievable. We have accepted it because, we've been taught that we don't feel the speed because we don't feel the rotation, but the rotation is very, very slow. We rotate every 24 hours at 0.0007 RPM. It's extremely slow. And that's why we don't feel any centrifugal force. But it's another whole other deal to think that we are going at 107,000 kilometers an hour. That's 67,000 kilometers an hour around the sun. That's incredible speed. and that is absolutely imperceptible, and no one has ever managed to measure it. That people must know. They have tried, oh my goodness, Michael Small experiments, Dayton Miller, they're all mentioned in my book, and they just failed to measure this incredible speed. And Einstein was he went into a panic mode when Dayton Miller repeatedly couldn't find this speed they were expecting. So we have no proof for the translational speed around the sun. We don't have it. We have very, very repeatable scientific experiments of the rotation of the Earth, the Sagnac effect, and other things. So these are two separate things. Absolutely agree that we rotate, because every single planet we see, every sun or moon, they all rotate. I mean, let's use logic. Of course, we rotate. I'm saying this for flat earthers, who say that we don't even rotate. And to geocentrists, old-fashioned geocentrists that say that Earth is completely mobile, that doesn't make sound sense at all. And then, of course, the distance to the stars. I mean, the distance to the stars is absolutely ridiculous when you think about it. We have the 19th most brightest star, called Deneb, 19th brightest of thousands of stars. That's supposed to be, well, they actually don't know exactly, but they estimate a range from 2,600 light years to 3,200 light years. I mean, just take a calculator and look at how far that would be. And so how far, but we can see it with our naked eyes, the 19th brightest star. But we can't see, and then the absurdity is we can't see with the naked eyes our closest star, Proxima. That's too dim, but that's 4.2 light years. So there are so many absurdities in the claims of the star distances. It all makes more sense if they're closer.
Okay, Simon, as I said, we are out of time. How can I follow your work?
You can go to the TYCHOS forum where we keep discussing the model. We have it's becoming a quite active forum, actually. You can obviously go to the website and find the book we'll soon have 7 or 8 language versions. It's in Russian, Dutch, soon in Portuguese, and in Italian and French. So it's for everyone to even read in their own language now, for many people. But especially the TYCHOS forum, it's all the updates, everything, especially with the TYCHOSIUM simulators has become very popular now, and people want to see this and that. So we are improving that every day. Of course, it's not ready completely yet, but it's remarkably accurate. And that's what has to be said. The TYCHOSIUM works. It is absolutely equivalent. It shows these planets and stars where they have always been seen.
Simon Schack, thank you for joining me in the trenches.